Some of the questions we have about the size of a minimum vertex cut or minimum edge cut were answered by Menger in the construction of what is known as a separating set. A set of vertices is said to separate U and V, two vertices, if U and V belong to different components after you take away S. All right, wait a minute. If S separates U and V, then U and V have to not be adjacent vertices, and S has to be a vertex cut, because we end up with G minus S being disconnected. Hey, wait a minute, that means that the size of S is bigger than or equal to the minimum necessary size for a vertex cut. So I have two vertices identified in a graph. I take away these other vertices S, end up with a disconnected graph, and U and V are in separate components of it. There are lots of different sizes for S, yes? Anything bigger than n minus 2. Leave U and V and take away everything else. But at least K of G. So if I had the smallest such, UV separating set, the one of minimum cardinality will be a minimum UV separating set. How do I figure out how many such sets exist in a given graph for any particular pair of non-adjacent vertices? Oh, no, not how many different sets, how many different vertices. In other words, how can I figure out the size of S? Hmm. I need, just for the moment, to draw some sort of a picture so I at least can hang my hat on some things that are going on. So I have the vertex U over here, the vertex V over here. And I've got some graph with a bunch of other vertices. All I know is that there is no edge directly from U to V. They have to be non-adjacent. If U and V are already in different components of G, then G's not connected, right? I'm done. S is 0. That's boring. So assuming that my set is connected, my graph is connected in the first place, then there's a path from U to V. So if I write a UV path, I write it U, which is vertex 0, then vertex 1, vertex 2, all the way up to vertex k minus 1, then vertex k, which is V. That's the way we wrote a path previously. So far, so good? All right. So somewhere in there, between U and V, I have these other vertices, V1 to Vk minus 1, right? I put them in between U and V just for the moment. But remember, since the way I draw a graph doesn't matter all that much, they could be all over the place. Doesn't matter. I'm going to call those the internal vertices of the path. If you think of a path as a graph itself, then it's got two vertices of degree 1 and a bunch of vertices of degree 2. All the vertices of degree 2, those are the internal vertices of a path. So I just think about the part that is the path. It's got the two end vertices, U and V. Everything in the middle, that's an internal vertex. I know there is at least one path from U to V. But there could be more, right? There could be lots more. I want to look at paths that have no internal vertices in common. P1 and P2 UV paths in G are internally disjoint if the only vertices common to both P1 and P2 are U and V. In other words, P1 and P2 do not have any internal vertices in common. Now, it may be that there's no way to do this. It may be that there is only one path from U to V. It may be that the paths all share something because there's a bridge somewhere along the way. It may be that there's a number of vertices in common and then it splits off into several different branches. But if there are internally disjoint paths, that's what I mean by it. They may or may not exist. And if I have a whole bunch of these, instead of just two, I could have a whole set. Then the only vertices any of them have in common are U and V. Any pair cannot share. And then we'll just call it an internally disjoint set of paths. I won't use the word pairwise all the time, but that's what we mean. We mean nothing shares an internal vertex. If I had two internally disjoint paths, then U and V must be on what? A cycle. Because I take one path from U to V and I take the other path from V to U, and they never share a vertex in common. Fabulous. All right. So far, so good. How the hell do these two concepts go together? Because it sure as hell doesn't look like a separating set has anything to do with an internal path. So let's suppose I have two non-adjacent vertices in a graph. The minimum size of my UV separating set, S, is exactly the same as the maximum number of internally disjoint UV paths. All right, what the I beg your pardon? I have an intuitive idea of why this should be true. But that comes from looking at a whole bunch of pictures. So let me start with a picture. Page 126. U is on the left, V is on the right. There are some dark edges here, bold-faced edges. Please notice those bold paths have no internal vertices in common. They are internally disjoint. And there's no other way to get from U to V that doesn't overlap one of those somewhere. By the way, these three paths are not unique. There are different options in all of them that I could take. But as I go from left to right, at no point can I get more than three different internally disjoint paths connecting U and V. Let that, play with that and see if you buy that. A couple of you are nodding. Some of you are still looking at this graph like it mortally offends you. I mean, this middle path, I could have gone down instead of up, right? But I couldn't have gone up again from here because I run into this path across the top. If I go down and across and down, I can't go down again. I run into the path on the bottom. So my choices are restricted once I decide my first UV path. Once I have that, then I have to look at what the consequences are. I've named a vertex on each path. W1, W2, and W3. If you remove W1, you're no longer able to get from U to V across the top path. If you remove W2, you're no longer able to get from U to V across the middle path. If you remove W3, you're no longer able to get there across the bottom path. I've cut out all the possible ways to get from U to V by removing three vertices. And one vertex must lay on each of the internally disjoint paths because that's the maximum number of different ways to get from U to V without overlapping a step. I saw this picture and I must have drawn those bold-faced lines 20 or 30 times trying to get different options. Could I find more than three paths from left to right? Because if I could find more than three, then I'd be able to need a fourth vertex. There'd be one way after removing these and all of their incident edges that I'd be able to get a connection. But that's a separating set. And it turns out to be a minimal separating set. Sure. There is a lovely biographical sketch of Menger on page 126, 127. I think you might actually find it very interesting to take a look at what happened in Menger's life and his connection directly to one of the founders of graph theory, Koenig. But I want this to work all the time, not just for one picture, which means I got to write a proof. And not just any proof. I have to write a proof by induction. I'm inducing on the size of G. Size is number of edges. What is the fewest number of edges I can have in a graph? 0. In which case, all the vertices are already separated, aren't they? That was nice. There are no edges for me to look at. There are no paths from U to V. I'm done. That was easy. Okay. I need an induction step. I am not particularly sure how to do this with simple induction, where I would go, oh, you've got K edges, let's look at one more edge. Because when I think about taking out a path that's internally disjoint, that's more than one edge, right? So if I want to remove something so I fall back down the ladder so I can make sure I can climb the next step, I need to do it more than just steps of one, which means I need a strong induction hypothesis. And that means I want to suppose that my result is true up to, not just at K, but everything up to and including K. I'm going to use M again. There's no reason to pick another letter. Okay, I just realized I said it one way and I wrote it another. I want to assume it's true for all of the values up to M, not including M, and then we'll try and use it to prove M, rather than trying to prove M plus 1. I want to show the next possible case. I've shown everything up to but not including M. That's my assumption. Let's see if I can show M. I need non-adjacent vertices, and I need a separating set. Let U and V be non-adjacent vertices in G, where G has size M, and suppose there are K vertices in a minimum UV separating set. I want to show that that means that there are k internally disjoint paths. I know we can't have more than k internally disjoint paths. Why is that true? I didn't say anything about the maximum degree of a graph here, maximum degree of a vertex. I said that was the number of things I needed to take away to separate U and V. But I didn't say that that was the degree of any one of the vertices in there. So unfortunately, no, but it is something we did say earlier, and I think I said that fairly closely thereafter. You should have written it down, because I can see it on this page over here. Yeah, why do I know it can't have more than k internally disjoint UV paths? If I have a k-sized separating set. Suppose there was one more path. Then when I took away the UV separating set, U and V are in different components. That means they're not connected to each other. How can I have another path? The size of my separating set is at least the minimum cut set size. It's a separating set, it's a vertex cut. I want to show you can't have any fewer than k. You can't have more than, you can't have fewer than, you better have exactly, right? So now I've changed the thing I want to show. The thing I want to show is that I have exactly k internally disjoint UV paths. Want to show I have exactly k internally disjoint UV paths. Fortunately for me, if there is only one UV path, then there has to be a bridge somewhere along that path, right? And that means if I take away the end of the bridge that is one of the internal vertices, I've disconnected. Poof, I'm done. So if k is 1, I can't have any more, I can't have any less. If k is 0, they're already disconnected. I'm done. So let's work on what happens when k is bigger than or equal to 2. Without loss of generality, assume k is bigger than or equal to 2. Because k equals 0 and k equals 1 are easy. Let's call our UV separating set capital U for the moment instead of S. And in this U, there's some vertex X. And that X is adjacent to both U and V. What does that tell you? Got to tell me something about paths. Well, it's one of the things that separates it. I'd have to take out all of U. But that means that X, I go from U to X and X to V. That's a path, isn't it? Okay. Hang on a second. Let's take that vertex out. I have a smaller graph, don't I? I have fewer vertices. Not only that, I have fewer edges. And in this new graph G minus X, the set U minus X is a separating set. If I chop out all of the vertices in U, then I separate U and V. But now I've taken away X, so there's one fewer thing to chop off. But I've already chopped it off of this graph and of the set, right? Wait a minute. That's a minimum separating set. What's its size? Size is K minus 1. Because K was the size of our minimum separating set. I am doing proof by induction. What have I just run into? The answer is not a contradiction. Underlined phrase is the key thing. This is a graph of size less than m. I've run into my induction hypothesis. In my induction hypothesis, what do I suppose? I suppose that Menger's result is true. And that means G minus X has exactly K minus 1 internally disjoint paths. But now you see why I couldn't do simple induction? I don't know what the degree of X is. When I took away X, I took away at least 2 edges. I may have taken away a lot more. I didn't go from M down to M minus 1. I went from M to M minus 2, at least. Could have gone to M minus whatever. Whatever that minimum degree is in this graph. Could have gone all over the place. What does that tell me about G? There are my internally disjoint paths, P1 to PK minus 1. It's a really bad looking minus sign, I apologize. What does that tell me about G? Jonah?
Doesn't it say that the minimum number of vertices in the UV?
But I don't know that for size M. I only know that for size less than M. And that's what we just used. What I need to show is that there's a kth path in G. There are only K minus 1 of them there. I want K of them in G. Where's my missing path? I know exactly what other path it is. Yes. And that's in G, and none of these paths can touch X, can they? Because those paths are in G minus X, which means this path is internally disjoint from all of the previous paths. In G, we have exactly K of them, Jonah, and I found exactly what was the missing one. But this made an assumption that there was some vertex X that was adjacent to both U and V. What if there isn't? Well, then I have some further refinements. Let me think about this. Maybe in my separating set, there's some vertex that is adjacent to U, but not adjacent to V. And there's some other vertex that's adjacent to V, but not adjacent to U. not minimum spanning, minimum separating. Now, please notice, this is not the exact opposite of the previous statement. So that means that there is actually a third case floating around here. We'll get to that one after this one. All right, so let me write out this spanning set so I have something to hang my hat on. W equals W1, W2, up to WK. At least one of those vertices is not adjacent to U. I don't know which one. At least one is not adjacent to V. I don't know which one. So let's make an induced subgraph. I'm going to start at U. And I'm going to look at all possible UWI paths. And you can't go through more than one of the W's. You can only go through one W per shot. So I've got U over here. And then I've got my separating set, W1, W2, da, 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 WK, right? And there's a path here and here and here. So that's the subgraph, well, the subgraph GI. I'm going to add a brand new made up vertex to this. The new vertex is called V prime. And V prime is adjacent to all of the W's. This combined thing, I'm going to call GU prime. Bizarre, right? I did this starting at U. What if I do it starting at V? I can do the same thing, can't I? I can go, hey, start over here at V, go to each of the WIs. And then add a new vertex, which I will call U prime, and make it adjacent to all of the W's. This piece is GV. This whole thing is GV prime. Page 125 is their version of this same picture. What do you know about GU prime? I don't know squat, man. Not true. Not true. At least one of the W's is not directly adjacent to U. So at least one of these is a path of length 2. Same thing over here. At least one of these W's is not adjacent to V. At least one of these paths has length 2. But that means that the total number of edges over there has to be less than M. Because I took away a bunch of edges over here. I took away K and more, didn't I? And then I added K. I added K edges, but I took away more than K. Because at least one of these paths has length 2. Same thing over here. I added K edges, but at least one of these paths has length 2, so I took away K plus 1 edges, minimum. What do you know about the size of each of these two things? Same thing. The size of GU prime and the size of GV prime must be less than M. I can use my induction hypothesis. But wait, there's more. Pick one, left side, right side, I don't care which one. Right side, from U prime to V, you have a separating set made up of all the W's. Menger's theorem. I have a graph of the smaller size. I assume my result is true. There must be K internally disjoint paths in GV prime. Same thing in GU prime. There must be K internally disjoint paths from U to V prime. Internally disjoint paths over here are from V to U prime, aren't they? Wait a minute. That means there's an internally disjoint path from U to W1 and W2 and WK. And that means there's an internally disjoint path over here from V to W1 and WK, aren't they? Glue them together. You have internally disjoint paths from U to V. But every path that goes to V prime, the last edge in it goes from WI to V prime. Every U prime V path its first edge goes from U prime to VI. Glue the paths together at VI. Sorry, WI. I have to think about what the remaining possible option is for my separating set. But I'm up against the wall, so that's what we'll pick up on Monday. There's a reason I'm going through this proof. It isn't just because I'm sitting here being a dick. It's because I keep talking about induction arguments in every class, and then I say, but they're too complicated, we're never going to do them. Screw it, we're doing this one. Because it is nothing more than understanding the drawings that we make. Menger was brilliant about this. Once I saw the drawings they put in this textbook about how to explain this, I knew I had to show it. I will see you all on Monday. And yes, I promised to enter the grades from this homework in the grade book on Canvas, which I forgot to do.